Let me introduce our next speaker. We have Yiyi Liao coming from Liao University, where he's a professor, who has also did a PhD in CVPR, who went to beautiful Germany to do her postdoc with Andreas Geiger, doing very influential work in 3D generation. She's been serving as program chair of 3DB, I think, recently, and we are very much looking forward to your talk about canonicalized 3D generative models. Thanks for being here with us.
Okay, sorry for the technical issues, and thank you so much for having me here. And I'm very excited to share some of our recent works on 3D generative models. So 3D content, of course, despite the recent very powerful video models, I still believe that the 3D content, they are of great value. For example, in AR and VR devices, we need 3D content to be efficiently rendered on the mobile devices as well, right? And then also for 3D, it's very important that if you want to do interaction, especially for like long tail or out of distribution scenarios. So this is one simulator we built for autonomous driving based on 3D Gaussians, where we can, because everything is in 3D, we can easily manipulate the scene to create, for example, safety critical scenarios by inserting cars interacting with the ego vehicle. For example, here we create scenarios that we have cars attacking the ego vehicle to create such safety critical scenarios. And I think there is also one very interesting aspect of generative models, which also aligns well with the topic today for this session. That is generative models for computer vision or for recognition tasks. So if we, as human, giving such a 2D image, we can easily imagine how the corresponding 3D object looks like, right? We can easily imagine the corresponding 3D object. And based on this imagined 3D object, we can do analysis by synthesis, right? So based on how the 2D image is generated from this single 3D object, we can analyze, for example, its camera pose. If we know how the object is posed in 3D, and then we know how the object is projected to the 2D space, then we know the orientation of the object. So by this, in this analysis by synthesis fashion, we perform object pose estimation. But then the question is, in which coordinate system the object is generated matters in this case, right? And before we start diving into the generative models, let's take a look at the different choices of coordinate systems that may be used. So here is a figure that I took from a famous psycholinguistic, which describes like the normal coordinate systems that we would use in our daily life. For example, we could use this absolute coordinate system, which is kind of like defined for Earth on the Earth, which is same for everyone, which is this absolute coordinate system. And with this absolute coordinate system, we may describe that the ball is east of the tree, and the tree is west of the ball, right? And then there is another coordinate system that is so-called dialectic coordinate system, where we define the coordinate based on our own observation. So let's say a human standing there in front of the tree and the ball, and then he may describe that the ball is to the right of the tree, and the tree is to the left of the ball. And then we can consider a third, one more coordinate system, which is the intrinsic object coordinate system, right? In that case, we define the coordinate system based on the object's its own orientation. And in that case, we may say that the ape here is to the right of the bear, and the bear is to the right of the ape as well, because they are facing forward different directions. So here, the left and the right and up defines how the objects, they are oriented. So in that case, what the psycholinguistic tells us is that the orientation, the coordinate system matters for recognition. And what I want to say is that it also matters for generation, because if we, for example, if we want to do what's called analysis by synthesis, then we also need to know how the objects are generated, in which coordinate system they are generated. So let's first take a look how existing generative models, they generate objects, right? So this is one example from the very recent work, Stable Virtual Camera. And there we can see that giving the three images on the first row, we can generate like 360 oriented objects, videos from these images. And what we can observe here is that they start from the camera pose that we provide and then orient for 360 degree, right? So I think this could be considered as this dialectic way of generation. So based on what you observe, you generate, with respect to this viewpoint, you generate the 360 degree result. And then we also have state-of-the-art 3D generative models, for example, Trellis. And with Trellis, this is what you obtain. Given the same three set of images, you get objects generated in their own coordinate systems independent to the camera viewpoint. But what you observe is that they face different directions. For example, the chair is facing towards right and the elephant is facing towards left. And in that case, we can think that the objects are still generated in their own intrinsic coordinate system, which is independent to the camera pose, but they're actually not aligned, right? And in that case, it's not that helpful, or it's not that convenient if you, for example, want to put objects into some things that you generate, or if you want to have do analysis by synthesis to determine the object pose by looking how the objects are generated, right? So as human beings, it's very easy for us to imagine objects in this intrinsic and canonicalized object coordinate system. And then we can do like analysis by synthesis to determine the object poses. So what are we missing here? And the answer to this is the canonical pose, the canonical space, right? So before we dive into this, like the cross-category canonical space, let's first look at some examples for single-category 3D generative models. So this is early work we did in 2020, where we extend NERF to GAN, like 3D GAN that it's called graph, right? And then we are able to generate from 2D images, we're able to learn a generative model that generates object level, generate objects for a single category. And the idea is also very simple here. Instead of training a single network to fit one object, we learn this generative model that takes as input a noise vector, and then also takes into a sampled camera pose to render 2D image. And this 2D image is then fitting to the discriminator to say that should be like a real image, right? And what was actually quite surprising back then is that despite there is no regularization on how the object should be generated, they're actually posed in the canonical space. So here are the early results that we obtained from graph. So why is this the case? We were actually a bit surprised, because if you look at the camera pose distribution, so for this car example, it's actually a symmetric problem, right? The camera poses, they are sampled from a hypersphere where the car can be placed in any orientation, and you can also get the correct object. But on the right case, that's the camera pose distribution for the face, and in that case, it actually makes sense because this camera pose, they are defined in a specific region, which is defined with respect to a canonical face. And you are sampling from this camera pose distribution, which means that you have to generate the face in that location to be able to render the images correctly. But for the car case, I think the reason is that we have positional encoding in the network, and then the network figure out that I can just generate the cars along the X and Y and Z direction, which we use as input to the position encoding. So that's very interesting finding back then. But the key message is here why it works is that we know the camera pose distribution, especially for the right case, right? For the right case, you define this camera position with respect to something canonical, and then the model also learns to place the object there. And later on, for example, EG3D, they even further improve this by detecting the human face and so that we obtain accurate camera poses for each image, for each real image. And then we simply sample from this distribution to render the images. And that's why it even performs the geometry. But for like in the wild data, it's just very hard to obtain or predefine a camera pose distribution for the 2D images. And in that case, what can we do? So a naive idea would be that we simply learn the camera pose distribution jointly with the generative model. And if you think about it, it's actually a highly ear pose problem. Why is it challenging? Because the generated object poses and the camera poses, they are entangled in the 2D space, which leads to an infinite solution space. For example, we can consider this spectrum. On the very left side, we have the ideal solution where we have the objects generated in the canonical space. And then we have the camera poses also correctly recovered. And then on the very right side, we can consider this case, which also provides us the same 2D image distribution. But in this case, what we do is that we place the camera at the same location and just we change what is generated in the 3D space. For example, we can generate a planar structure and put the car on the plane. And then this also leads to the same 2D image distribution, right? And in that case, if we simply learn this joint distribution, then what you obtain would be something like degenerated to a 2D or 2.5D, because you're not able to correctly recover the 3D real camera pose distribution. And our key idea in this work, TAF, is that we can actually get a canonical pose, a canonical space from the generative model itself. And then with this canonical model, we then develop a pose solver to estimate the pose of each real image. So the key idea is that we, in addition to the normal generative model, we additionally learn this feature field such that it's agnostic to the appearance of the objects. And based on this learned feature field, we additionally we extract the data set mean by feeding just a 0 into the generative model to get a 3D canonical feature field. So this allows us for each 2D real image, and when we can have this 2D, 3D pose matching problem, and if we solve this, we get the pose of each real image. And here is more illustration for this process. So we first extract all the features based on Dino, and then we have this, we learn this template feature field. So this template feature field serves as a canonical space for us to solve the pose of each real image. And here, the poses illustrate the pose that we estimate based on the template. And of course, actually here, one detail that I'm not going into is that if you directly solve using normal 2D, 3D pose matching, this would not work because it's just a single template for all the real images. So what we do here is we kind of discretize the space for the pose, and then we develop an efficient but a global pose solver to obtain the pose. So with this, we are able to recover the complete objects because we are now able to have this canonical space and resolve the pose for all the real images. And then we also have the photorealistic 360-degree image synthesis, like this. So on the bottom right is our result, where we can generate the 360-degree objects because we are able to correctly estimate the camera pose. And it also applies to other categories like cars and also like airplanes. So if you think about it, what we did in this work is actually jointly performing generation and pose estimation in this single framework. And here we further show some pose estimation results, where on the first row, you see the real images and their dynamic features. On this pose row, it indicates how the templates are rendered to the target pose to match the feature of the real images. So that's about the single category generation, right? The question is, can we further scale this up to more categories, right? And the answer is that now we need cross-category aligned data, because before we were working on a single category and we can solve this using just one single template. But now if we want to really focus, work on more categories, we want to work on more data, now we need to align all the objects from different categories, right? So this is super hard to be addressed if we have only 2D data. And what we then looked into is the 3D data sets. So for example, we have the great Objectverse dataset and also the follow-up like Objectverse XL. But if you look carefully, you will find that objects in the object-verse, they are not aligned in their orientation. So what we propose is a new dataset or a subset version of object-verse, where we corrected the orientation of all the of a subset of object-verse datasets to make sure that they are all orientation aligned. And then we think we were asking, how can we do this like more efficiently, right? So nowadays we have very powerful like visual VLM models. So can we actually directly solve this using VLMs? So we looked into, maybe we can just feed into like some images to Gemini and ask Gemini which one is the front view. And we actually, we first did this. So this task is actually not that, like we do not need to feed a crazy amount of images to Gemini to identify the front view. The reason is that for many objects in Objectverse, they are usually placed on a horizontal plane with only the yaw angle that's like different. And usually the yaw angle has only like 4 options, like 90 degree between each, right? So what we can do is that we can simply render from these 4 viewing directions and ask Gemini which one is the front view. So we found out that Gemini actually works well for many of the cases. For example, for this chair, you're able to identify the front view. It's able to identify the front view is A. However, it's also very challenging for many other cases. Like consider this seahorse here. What Gemini identify as front view is A. But this is actually, if you consider the definition of front view where the head should be looking front, right? Then the correct answer should be D. So this is a very challenging case. And then there are also other data sets in Objectverse that they're actually not placed in the nice way that is only with yaw angle difference. And in this case, there is actually no correct answer in these 4 images that we provide. And in those cases, we have to manually correct them. So what we propose to achieve the efficient like orientation alignment is that we first use Gemini to go through all the objects, and then we check the results to do manual correction. So this leads us an orientation aligned dataset containing more than 14,000 objects. So this may still seems not that much comparing to the original scale of Objectverse, but we think this should be the largest dataset of the orientation aligned objects. And we also plan to release this in the future. So with this orientation aligned dataset, we then again looked into the error rate of VLMs. So here shows the error rate across different object categories. So there are some objects that VLM fails all the time, like for these thin objects. And then there are some cases that VLMs fails with quite high error rate, like for example, there are objects with orientation ambiguity, and also for the seahorse that I showed before. But of course, there are also cases where it works just pretty well. And with this like 14,000 objects, we can then fine-tune existing generative models to make them orientation aligned. So here I show some image to 3D object generation results from Chalice. I didn't show the original image here, but what you can obtain, these are the generated 3D results. What you can observe is that they are actually placed kind of in arbitrary orientations because of the misaligned original Objectverse datasets. And what we, after the fine-tuning with these 14,000 objects, this is what we obtain for the same objects. And you can see that they are all nicely orientation aligned to the same direction. So we also observe some very interesting cases. For example, if we look into these 2 objects, so they actually aligning the orientation of the objects may also sometimes improve the performance, the generation performance itself, right? Because this kind of reduces the variation of your ground truth data space. So this leads to sometimes improved performance, but it's not always the case, because also one limitation could be the relatively small scale of our data set. So if we scale this up further, I think the performance can be even improved further. And this dataset, orientation aligned dataset, can also be used to fine-tune other generative models like this. So we just show that we can also use it to fine-tune image-based multi-view generation models like Wonder 3D, where we're also able to align the objects generated by Wonder 3D. And with this capability, now we are able to perform what we showed before, right? For these three images, now we are able to generate objects in aligned orientation. And now we are able to perform object pose estimation in a zero-shot manner by taking these generated objects as template to perform zero-shot intrinsic pose estimation simply using analysis by synthesis fashion. And we can also apply this to more categories. And another application could be the image editing. For example, if you want to insert an object that you generate to existing 2D or 3D environments. Without the orientation alignment, it's just really hard. You need to manually adjust it to the designed orientation. But with this, with our model, you know in which pose the objects are generated. And that's why you can directly insert it into the scene by simply drawing a direction where the object should face to. So in this case, we show a very simple example, like giving this image, and we provide an input like 2D image, and with this object, this piano image, we generate a 3D asset with known with the orientation that we know, right? And then we draw a line to indicate the forward direction of this piano that we wanted to pace into, and this is what we obtain. And of course, the size and other properties should be determined like by manually or using large language models. So once we are talking about image editing, then people may wonder, okay, existing 2D generative models, they are really great at image editing. For example, the very recent Flux One context, right? This is very impressive. So we also tried it on this example. So it's really impressive to me what it can achieve. For example, if we say add a toy dinosaur in the middle of the room, this is what we obtain. It works really well. And if we say make the toy dinosaur facing me, it also works. But if we say place the piano with it back facing the window, this is what we obtain. So it kind of decides, okay, it's kind of a long tail scenario, right? If you want to, in this image, if we want to place the piano with its back facing the window. So it didn't work out. We also tried the same prompt and the same image with GPT-4o, and this is what we obtain. So it works, but GPT-4o decides that the room layout needs to be changed significantly to be able to put the piano there. So of course, with our 3D assets, it's very easy to place the piano there because you know the 3D assets, right? So yeah, that's about the object level generation that I want to talk about. And then I would also like to quickly share some thoughts on scene generation. So for objects, we know that it's good to generate them in the aligned object space. But for scenes, what can we do if we want to do 3D generation? And if you just look at the scene images, it's just really hard to find a way to align them just like objects, right? And it's true that for objects on the left, as shown on the left, we can have this object intrinsic coordinate system that we define its forward-facing direction, its left direction, and its upward direction. And this definition is independent of the camera poses, independent of how we view the objects, right? But for scene, it's really hard to define a unified scene coordinate system. And also what usually matters the most is how we view the scene. So maybe we can canonicalize scene generation based on camera coordinate system. And what I also want to argue is that indeed, maybe there is just no need of absolute board coordinate system for downstream tasks. So I think there is one way to unify the scene generation is to use for example, like the one unified absolute word coordinate system for them. But this is not how humans perform daily life, perform tasks in daily lives. For example, for this absolute word coordinate system, there is also so many ways that we can define it. For example, we can define the origin on the Earth. We can even define it on the moon. And so we can define here and there. But really matters for our daily life, for how we interact with the world, for human and for robots and for autonomous driving cars. What matters the most is how we are with respect to the environment. So this relative coordinate system matters the most, right? So if we look at some autonomous driving like systems, how they work, they actually, if you look at the BEV image on the right, what matters the most is how the ego vehicle is there with respect to the world, right? So we can kind of like canonicalize everything based on the ego vehicle, based on the observer itself. So this might seem straightforward, so we can use camera pose to canonicalize what we do for scene generation, but there are still different choices. So this is just very simple illustration of how projection works, right? So we have this scene, and then we project it into an image plane, and we have here like world coordinate system, image coordinate system, and camera coordinate system. So there are two options still. We can define everything in the image coordinate system, where we define everything in the 2D space. But we can also define everything in the 3D camera coordinate system, right? So there are still these two choices. So which coordinate system should we use? And I don't have a very good answer to this here, but we have tried both. So what you can do, if we generate everything in the image space, you can generate a 3D scene formulated as multi-view 3D GS generation, for example. And then you normalize it with respect to, for example, like the first frame. And then you can also generate everything in the camera coordinate space, which does not involve the perspective projection. But I think there are trade-offs for both options. So for the left option, what we the advantage is that it's very easy to reuse the 2D price for this generation process, because it's kind of like a 2.5D generation task, and you can reuse 2D price for the generation. But however, in order to obtain the 3D scene afterwards, you need to do the nonlinear perspective on projection, and you need to then concatenate all the content you generate across scenes, and this may then lead to inconsistency. And on the right, because you directly generate in this camera coordinate space, you generate everything in 3D directly, so it does not involve nonlinear perspective projection. However, it's also not so straightforward to reuse the 2D price in this case. So I'm not going into details, but I just want to show you some results that we obtained with these two paradigms. So for the first one, we have a paper named Prometheus, where the key idea is how we reuse the prior of 2D models to generate 3D content for text to 3D generation. That's why the name Prometheus. So here, what we did is that we extend existing stable diffusion to generate multi-view 3D Gaussian. And what we propose is that we additionally learn RGB D-latent space instead of RGB latent space. And we learn this cross-view VIT to be able to align the multi-view latent. So here, it follows the idea of this image space alignment, where we define the first frame as the normalized frame. So the origin is defined based on the first frame generation. And because we are able to reuse the 2D prior here, we're able to perform text to 3D generation with single, it's kind of just like a standard LDM model. And then we can perform like 3D GS generation in this model. But however, like as I mentioned before, because now we generate everything in the image space, and we need to do the on projection to concatenate everything in 3D. So when we have large viewpoint changes, this may lead to multi-view inconsistency. This is some failure case that we obtain. And that's why we also tried the other choice for this camera space 3D generation, where we normalized everything with respect to the camera pose, but we stay in the 3D space. And here, like we also like trying this is also one of our very recent work which is not archived here. So here what we want to do is that we generate everything in 3D, but because of the lack of 2D pry, it does not have very good quality, and then we further leverage the 2D models to refine the generative 3D results such that it provides us high quality and also being able to achieve such out of distribution camera control because that we have the explicit modeling of the 3D. With that, I would like to conclude my talk. So some take-home messages. So a key message that I want to present here is coordinate system matters for 3D generative models. And we should generate 3D objects in the canonical space whenever possible. And this also enables solving downstream tasks like zero-shot object estimation. And also canonicalizing the objects can reduce the data variation. This may further improve the performance of the generative models. But for scene generation, we lack a canonical space, but this can be aligned using the camera coordinate system, preferably in the Euclidean space instead of in the camera space. And I think for like considering the trade-off for this 3D generation and 2D pry, I think if we want like the designed outcome is in 3D, then it's better to generate everything directly in 3D. But in that case, how can we effectively leverage 2D pries for that generation? It's still like it's still to be explored, and I think there are still like much more that we can improve there. And lastly, I'd like to thank all my collaborators and thank you all for your attention.